I will now talk about statistics in metrology. And what I said about the mathematics being not the main problem, but what the mathematics means is even more relevant in statistics, where the equations are normally very simple, but the interpretation is not straightforward. One application of statistics in metrology is to improve or correct errors in computer-made forecasts, numerical weather prediction maps. And what I will present here is a technique that helps us to achieve that. But before coming into the main topic, I will just pose the problem we have. In the lower left we have a value from the computer. It's presented in a grid point, but it actually represents an average over a grid point box. That is the forecast value. And this should then be compared to or verified with the observation from a particular station somewhere in our region. That is a point. So what we want to do is to improve this forecast so that it fits better with the observation. But to understand this problem more deeply, I think we must introduce an intermediate step, a bit abstract. And that is the following. So here we have, again, the same box, but now this box is filled of observations. So what we can create here is an observation which is an average of all these observations. And that makes it more consistent to compare a grid point average with an observation average. And the next step is to compare this average with a specific existing observation that we have. And if we have this separation, we can identify three sources of differences between the forecast and the observation. And the first one is between this mean and this mean. And that is systematic errors because the physical model, computer model is not perfect. It has systematic, minor perhaps, but still systematic errors in the description of the physical processes, for example. That might lead to over or under forecasting of this parameter, for example, temperature. There might also be systematic errors because between these two, because this is an average over several stations, or at least imagined stations. And this is one particular station. And this the location of this station might be quite different from most of the stations here. So we have a problem of the representativeness of this station for this average. So these are two systematic differences we have to think about. But there are also non-systematic differences. And one is between, again, the grid points average and the observational average. And that is what we normally think about when we talk about forecast errors. It's large-scale systematic errors, non-systematic errors, the arrival of high or low pressure systems, of cold and warm fronts. They are too strong, they are too weak, they come too early, they come too late. That introduces non-systematic errors. And finally, between these two, the average of observations and one observation, there is also a source of small-scale subgrid variability, which means that they are not possible to resolve by the model, perhaps will never be, but it will still introduce differences between these two values on a non-systematic basis. And I will talk about all these, but concentrate on some of them. So the non-systematic errors because of synoptic noise is normally what we think about weather forecast errors. And here is a diagram where you have the root mean square error, the forecast range, and with increasing forecast range, the forecast gets worse. And a persistent forecast, it meaning the weather now will be what is in the future. This will reach rapidly a very high level of error, and I have put here the error of a climatological average of what you find in a tourist brochure. And this upper level is the square root times this climatological forecast. And as it so happens, this persistence forecast will end up more or less with the same skill as a pure guess. And this computer-made forecast will also ultimately 5, 10, 15 days ahead be no more valuable than a guess. So also this forecast will approach this higher error level. And that means that at some stage, depending on the model of course, but depending on the parameter, one single computer forecast will be worse than a climatological average or what you can find in a tourist brochure. So these are the error development of non-systematic errors, and in the following I will work on forecasts which are in the very short range, where you can more or less ignore this large error growth and concentrate on the other aspects. The second non-systematic error is the small-scale variability. It might be sea breezes or even wind gusts that will make differences. And when I worked in England, we made a test. We compared Gatwick Airport observation with observation from Heathrow. And under the assumption that the observation from Gatwick is very close to Heathrow, so as a forecast for Heathrow. So we have a perfect forecast, the observation for Gatwick, and how will that verify for Heathrow? I don't have the values from that investigation, but I have something similar we used in close to Berlin. So we have an observation from Potsdam, and then how well does that serve as a forecast for nearby Lindenberg? And what we found is that they will on average differ by less than 1 degree, which is not much, but it's not zero. And that means that when we verify weather forecasts, we cannot expect ultimately to have 0 degrees in temperature error. There will always be this small scale which we will never be able to catch. So what we should aim at is errors down to 1 degree and perhaps slightly lower, but we cannot come very much lower than that. So these were the non-systematic errors, and I will now talk about the systematic, which we can statistically attack and perhaps dampen or even get rid of. Yeah, before I do that, here is another example. It's a forecast verification of temperature, and a common error is that when you have diagrams like this showing the error growth of temperature forecast, you assume that at initial time the error is 0. But as you can imagine, that if you extrapolate this 6, 12, 18, 24-hour forecast backwards, the initial error is actually in this case 0.6 or perhaps even more. So it's another indication of that we cannot expect that the errors at initial time are necessarily 0. We have observation errors, we have other things that make them non-zero. Now coming to the systematic ones, this is where you have these two the data can be compared because they are both averages. And if they are different in a systematic way, it might be because the physical parameterization of the model is not perfect, and it's natural because it's difficult to exactly mathematically model effects of in and outgoing radiation and moisture and etc. So then we have systematic errors, differences between forecasts and observations. And one obvious way to think about this is that we have a bias, a flat bias, a mean error. Something is too much or too little. And here is an example where we have on the x-axis the forecast temperature, and at the y-axis the error. And we have now 4 forecasts, and one of them was too cold, one had no error, and 2 were too warm. And on average you had a mean error of some magnitude. Now, does this mean that we have a systematic error of this type? Perhaps not, because next time the 5th forecast might come up here, and the 6th here, and now it's warmer. You can see that it has become warmer, higher temperatures, and now the errors appear much higher. So does this mean that now that the bias has changed from a rather low value to a much stronger value? Well, not necessarily, because we can also look at these 8 forecast verifications from this perspective. We have a systematic error, but it's not a flat bias, not a mean. It depends on the forecast itself. So the correction is now following an equation type like this: A plus B times the forecast, where A is the difference here and B is the slope of the line. So it means that the forecast systematic behavior reflected in A and B remains more or less constant, independent of the forecast value itself. And this is what can be used in the Kalman filtering. The Kalman filtering is a self-learning system where you constantly update your old knowledge. And now imagine that at some stage the system has reached the conclusion that the arrows are lining up along this line. And so here you have the last numerical weather prediction forecast, and it allows you to forecast the error. So the expected forecast failure can be predicted and corrected for. You subtract or add this value that is given. But then the forecast is verified, and it turns out that the forecast of its error was good but not perfect. So it is on a slightly higher level than predicted. And what the Kalman filter does, and I have no possibility here to go into the details of the Kalman filter, but this is how the operational setting works. The Kalman filter modifies A and B. A is lifting or sinking the line, and B is slightly rotating the line. And depending on if this red value is close to the y-axis or far away from the y-axis, one of these will dominate. If this one is close here, it will be mainly a translation. If it's far away, it will be mainly a rotation, changing B. So what the Kalman filter will determine is new values of A and B, slightly different from the previous. Not entirely covering the observation, but approaching the observation. So now we have a new error equation that can then be used for the next forecast. And the next forecast will be here. It will give a correction of the opposite sign. And we apply that. And then comes the verification, and it's almost perfect, but still not perfect. So now the Kalman filter makes a new slight modification. And if the verifications continue to appear scattered around these lines, not much will change. But if these red balls start to appear in new directions, the Kalman filter will need 3 or 4, perhaps 5 days to modify, to actually turn into a new direction by step approaching the new values. This was now a two-dimensional A plus B times the forecast equation, and it's you can have 3 dimensions or 4, and there's a fundamental difference between the first approach, where you just have a mean error, compared to these 2 or 3 or 4 or multi-dimensional systems. Now I will show that now with an example from Lapland in the winter 15 years ago. I think the models have improved since then, and there might be less need for Kalman filtering, but I don't know. I will at the end show you a fresh example that Kalman filtering obviously is still needed. So here we have 1 day forecast for Kiruna in northern Lapland, and the dashed line is day 1, the 24-hour forecast, day by day from October 2001 to January 2002. And the dots are the observations. And as you can see, when it's mild, the forecast is not bad, even good. But when it's cold, it is much colder than what the model can produce. A one-dimensional filter. And now the Kalman filter is the full line. As you can see, when it starts here, it's learning, it's doing day by day learning. So now he's quite happy, he doesn't do very much. But then when he comes down here, he discovered that he has to cool the forecast. But when he had learned that, it's time to go back. And now he continues to cool the forecast without being aware of that the forecasts are quite good. And when he then learns that he does not have to cool them very much, then it goes back into a new cold period where he is now again forced to cool the forecast. So he always out of step with the development, and that is not an efficient way to correct the forecast. But if you apply this two-dimensional approach, that the Kalman filter corrects the forecast depending on the forecast itself, then again he starts in the mild period with not doing that very much, but then when it gets cold, he has the mathematical ability to connect that to the forecast itself. He can do a much better job actually cooling the forecast, and then when it goes back to mild, he is back in another region of his equation, and like this one, and more or less can leave the forecast unchanged. Then for the next cooling period, he is back, and just because A and B in this equation remains more or less constant, there is no problem to cool when it's cold and made it unchanged when it's mild. So here the corrections are not out of step. And another thing that you might appreciate is that apart from improving the forecast much more, it has also not only corrected for a systematic warm bias, it has also made the Kalman filter forecasts have the same variability as the real atmosphere. So it's not only a matter of improving the forecast accuracy, it also to create forecasts that behave similarly to the atmosphere, has the same range of variability as the atmosphere. And then finally, you have the representative effect. And here I have taken a case from northern Norway, where there is a lot of mountains, and the grid points in the model sometimes lie higher than the real observation, because the grid point resolution cannot resolve these narrow valleys that are typical for alpine or North Scandinavian mountains. So Tromsø is the forecast for Tromsø is obviously taken from a grid point at the high levels, because the forecast is quite colder than the observations. But now the Kalman filter identifies this systematic behavior and corrects for it. And as you can see, does a fairly good job in warming the forecast when it's needed, and not warming it as much when there is not much cooling. So finally, in Petersburg last week, Suleiman, Alfred and I, we had a preliminary test of the Kalman filtering for Petersburg, and it's December, January. It's 1 day forecast from the best model in the world, the European Center model from Reading. And as you can see, the forecast, 1 day forecast for the temperature is not bad, but it's still not perfect. And the Kalman filter is starting to learn from here, learns to warm it by 1 degree. And then here he learned that there are some problems, but they are not systematic, so he does not do anything. And then in the last part of the period, it's able to improve the forecast by about 2 degrees to correct for mean errors about 2 degrees. And then finally, when it's quite mild, it doesn't do very much. So even the European Center model needs some Kalman filtering. But of course, models which are not that perfect, but need more work by the Kalman filter to remove systematic errors. And that is what I recommend people to apply. Thank you.